So it's time to introduce the last of the major circuit elements that we're going to deal with, and that's the inductor. So we'll do what we've done for all the rest of these. We'll start by basically laying out a basic definition for the inductor. And so what an inductor is it's a device for storing energy in a magnetic field within a circuit. The honest statement is that inductors are the simplest of our circuit elements to make. They tend to be the most difficult one to think about what's going on. So let's start by just how do you make an inductor? Well, it literally is as easy as take a tube, wrap your wire around a tube, you've created an inductor. Whether you keep the tube there or not doesn't really matter, right? So you could remove the tube and then you'd have an inductor with an air core. That's the picture over here on the right. If your tube was made out of iron and you left it inside the wrappings of your coil, then you have an inductor with an iron core. But notice that both of these pictures are literally just you have taken a wire and wrapped it around some cylinder. That's an inductor. Okay? So making them is easy. Describing them is a little bit more complicated. So in terms of what's going on with an inductor, notice we've got a current. Right? So we've got current flowing through our wires, and now we've created wire loops, right? So in wrapping the wire around a cylinder, we've created a series of loops. The current will create a magnetic field. That magnetic field will then generate a magnetic flux through those loops. So the physical quantity that defines an inductor is its inductance. Just like the capacitance defined a capacitor, the resistance defined a resistor, the inductance defines an inductor. And the inductance is given by the letter capital L, and it is the ratio of the magnetic flux to the current. So this is the magnetic flux piercing the loops of your inductor to the current being driven through the inductor. So you can see that the inductance is a measure of how much magnetic flux is generated by a given current. The higher the inductance, the more magnetic flux you get for a certain current value. So I know from Faraday's law, I can determine the induced EMF that I get by changing the magnetic flux through some loop, that's going to be equal to the change in the magnetic flux over time. So what I see is that in terms of thinking about the magnitude of the potential difference of my inductor, that's going to be given by delta phi over delta t. And again, if I solve this for phi, the magnetic flux, I get L times I. L is constant. Again, that just depends on how you chose to wrap your coil around your cylinder. I is the only thing that changes. So we can pull the L out, and I see that the potential difference across my inductor is equal to the inductance times how the current is changing with respect to time. So what Faraday's law tells us is that inductors are going to try and resist changes to currents that occur within your circuit. So if you have some current flowing through your circuit, and so therefore some current flowing through the inductor, and you try and change how much current is flowing in your circuit, the inductor is going to generate an EMF that resists that change. So as with all the rest of these fundamental quantities for our circuit elements, we can use the equation for the inductance to determine what the units are for inductance. And so since the inductance is given by magnetic flux per current, then the units of inductance are going to have units of magnetic flux, which in SI units are Webers, over current, which is amps. And again, this happens often enough that it's been relabeled as the Henry. So Henrys are SI units for inductance. And again, we will tend to see relatively small values. So you'll tend to run into values of Henrys that are less than 1 and often significantly less than 1. So Faraday's law was part of what we learned about electromagnetic induction. The other piece we put into that, of course, was Lenz's law. And Lenz's law told us that the EMF that was induced when you changed the magnetic flux through some loop acted to oppose that change. Well, the same thing's true for your inductor. The induced EMF in an inductor acts to oppose the change in the magnetic flux, which of course means it's trying to oppose whatever change you have in the current flowing through your circuit. We've zoomed in on our picture of the circuit around the inductor. So I've got the wire coming into the inductor. Here's my inductor, its circuit element. There's the wire going out. And initially there's some amount of current that's flowing to the right through that inductor. Well, there are two ways that I can obviously change that current. I can increase the current, which means that more current's now flowing through the circuit. That increased current will generate an increase in the magnetic flux through the inductor. And Lenz's law says that that's going to result in an induced EMF that will try to cancel out that increase in the magnetic flux. So this will be a back EMF generated by the inductor. On the other hand, if I decrease the current, so now there's less current flowing through the circuit, less current flowing through the inductor, less magnetic flux through the coil of the inductor, that will induce an EMF within the inductor that will act in the same direction as the current flow. So it won't be a back EMF. It will be an EMF that's trying to drive current in the same direction that the current is already flowing. So if you increase the current, you end up with an EMF from the inductor that is acting to try and decrease that current back to what it was. On the other hand, if you decrease the current flowing in the circuit, your inductor will generate an EMF that is trying to increase the current back to what it was. So in both cases, the inductor is simply trying to get you back to what the current was before you started trying to change it. Well, if fundamentally an inductor, its function is to store energy in a magnetic field, how does it do that? The energy stored in the magnetic field is just going to be equal to the magnetic potential energy stored up within your inductor. And so that can be calculated as 1/2 times the inductance of the inductor times the current flowing through the inductor squared. So the larger the current flowing through the inductor, the more energy you have stored up in the magnetic field.